Hi students, good evening. Welcome to this video session. My name is Samuel Chukwu Emeka, aka Sam Dumb for Peace. In this video session, we shall discuss your section 10.3 homework assignment. Section 10.3 deals with regression. When we find out that there is a correlation between two variables, what do we do next? Regression is actually the introduction to forecasting. So when we find out that there is a correlation between two variables, then we can use the explanatory variable or the predictor variable to predict the response variable, provided that the values of the explanatory variable are within the range of the data, are within the scope of the data. Please, it is required, it is recommended that you view the videos and read the notes, as well as the section in your textbook prior to viewing this video. As with all other videos, we are going to use technology to solve questions in this video. The technologies we shall use are my calculators and Pearson Statcrunch. Let's get started. Question 1. What is the difference between the following two regression equations? As you can see here, this lowercase b, this is like your the slope-intercept equation of a straight line. Actually, that is what we call the least squares regression equation. Or you can say line of best fit, or you can say least squares regression line, or you can just say the least squares line. This is for two variables, x and y. You can use this to make predictions if you discover that there is a correlation between the two variables. So usually you have y equal to mx plus b. You did that in algebra. Some people will say your mama ex-boyfriend. So y equal to mx plus b, where m is the slope and b is the y-intercept. The coefficient of x is m, which is the slope. So the coefficient of x here is b1. I know here it says b0 plus b1x. So, you know, some people will say y equal to b plus mx. b plus mx. Remember, m is the slope, b is the y-intercept. So in this case here, b1 is the slope and b0 is the y-intercept. In this case here, beta, this is beta, is the Greek alphabet. Beta 1 is the slope and beta 0 is the y-intercept. So this first equation here is for sample data, and this second one where you see the beta is for population. So the answer is A. Question 2. Suppose IQ scores were obtained from randomly selected siblings. For 20 such pairs of people, the linear correlation coefficient is 0.922. And the equation of the regression line is this equation here. Y hat is equal to negative 9.98 plus 1.09x, where x represents the IQ score of the older child. Also, the 20 x values have a mean of 100.28, and the 20 y values have a mean of 99.2. What is the best predicted IQ of the younger child, given that the older child has an IQ of 96? Use a significance level of 0.05. 0.05 is 5%. So when you're dealing with regression, if you find out that there's a correlation, then you check actually for it to be, when you have a correlation, that means the absolute value of the correlation coefficient should be greater than the critical value for the sample size, for the specific sample size. So the sample size is 20. The correlation coefficient is 0.922. The absolute value of 0.922 is still 0.922. Now, we are going to compare this right here, 0.922. As you can see here, 0.922 is a high value. So most likely you have a strong positive correlation between the two variables. So, but we are going to compare this value right here, the absolute value of this, which is 0.922, with the critical value of the correlation coefficient for a sample size of 20. So we click here to look at the critical values, and this is 5% significance level, 0.05. Sample size is 20. So you look for 20, and the critical value is 0.444. Because the absolute value of the correlation coefficient, 0.922, is greater than 0.444, because this is greater than this, and this value is positive, we now say that there is a positive linear correlation between the variables. So if you read your notes and the prerequisite videos, you will understand what I'm saying. So because this is greater than this, we say that there is a positive linear correlation between the variables. So if there's a positive linear correlation between the variables, as we can see here, we are going to use the linear regression equation, or the least squares regression equation. Okay, I've said linear regression equation, or least squares regression equation, or line of best fit, or least squares line. So we're going to use this equation now to make the prediction. So let me just pull up a calculator here. So because there is a positive linear correlation between the variables, my x is 20, because x represents IQ of the older child. Yeah, I'm sorry, x is not 20. I mean, the sample size is 20, but x is 96 in this case. Okay, we want to find the IQ of the younger child, given that the IQ of the older child is 96. So in this case, my x is 96, and I want to find the best predicted IQ, which is the y hat of the younger child. So we find that there is a positive linear correlation between the IQ of the younger siblings, younger children, and the IQ of the older children, that there is a positive linear relationship. So we're not going to predict, because that is the essence of this topic. If you find out that there is a correlation between the two variables, then you can use x to predict y. You can use the input to predict the output. You can use the independent variable to predict the dependent variable. You can use the predictor variable to predict the response variable. You can use the explanatory variable to predict the predictor variable. Okay, that is x and y. You can use x to predict y. So I'm going to just do 1.09 times 96 equal to, then minus 9.98 equal to. So this gives me 94.66. 94.66. Okay. Question 3. A sample of 40 women is obtained, and their heights in inches and pulse rates in beats per minute are measured. The linear correlation coefficient is 0.265. This is really, really small. I know it's positive value, but it's really low. And the equation of the regression line is y hat equal to 17.9 plus 0.890x, where x represents height. The mean of the 40 heights is 63.3 inches, and the mean of the 40 pulse rates is 74.8 beats per minute. Find the best predicted pulse rate of a woman who is 71 inches tall. Use a 5% significance level. So we have this linear correlation coefficient, the 0.265. The absolute value of this, the absolute value of 0.265 is still 0.265. Now, the sample size is 40. We're going to check the critical value of the correlation coefficient. Actually, this is Pearson correlation coefficient. Okay, critical values of the Pearson linear correlation coefficient for sample size of 40, and we compare it with this linear correlation coefficient of 0.265. So we click here, and this is at 5% significance level. So you look for sample size of 40, and you have 0.312. So as you can see here, 0.312 is greater than 0.265. If the critical value of the correlation coefficient is greater than the absolute value of the correlation coefficient, then there is no correlation, there is no linear correlation between the variables. And in the case where there is no linear correlation between the variables, you don't use the regression line to predict the response variable. You don't do that. Rather, you use the sample mean of the response variable. Now, you don't use the sample mean of the explanatory variable. Okay, the explanatory variable is the x, the predictor variable is the x. It's the same thing, while the response variable is the y. So you don't use the, when you find out there is no linear correlation between the two variables, then you don't use the regression equation. You don't do that. Rather, you use the sample mean of the response variable. You don't use the sample mean of the explanatory variable. The explanatory variable in this case, which is the x, is the height. The response variable is the pulse rate. So you use the sample mean of the response variable. And that gives us 74.8. That is what you use as the best predicted response variable. So you don't use this equation because you find out now that there is no correlation, there is no linear correlation between the two variables. So we're going to use 74.8. Question 4. Use the given data to find the equation of the regression line. Examine the scatter plot and identify a characteristic of the data that is ignored by the regression line. So what we're gonna do is we'll do a question with Statcrunch, then we'll do with my calculator. We do with Statcrunch, we do with my calculator. So let's start with Statcrunch. I'm gonna click on this, open in Statcrunch. We already have our labels X and Y, so we are good. So you go to Start. Let me pull this to be on the same page. Let's get this to be on the same page. So you go to Start, you go to Regression, you click on Simple Linear. For the X variable, select the X. For the Y variable, select the Y. And for this, you're not performing hypothesis test or confidence interval. So you just leave this as is. You just leave it as is. And then they didn't tell us to predict the Y. They just asked for the equation of the regression line. If they ask us to predict the Y, I'm going to show you how to do those when we see the questions like that. So you just click compute. You click compute. And this is what you have here as the linear regression equation right here. I mean, some textbooks, your textbook is writing it as y equal to b plus mx. Yeah, but you know, I know you're familiar with y equal to mx plus b. Yeah, but it's the same thing. This is the slope. The coefficient of x is your slope, which is now 0.8. And this is your y-intercept here. The constant here is the y-intercept. So it doesn't matter, you know, if you say y equal to b plus mx or you say y equal to mx plus b, it's the same thing. So, and that is the way your textbook wants it, like this. Round to 2 decimal places as needed. So this is 2.5 for the y-intercept and 0.8 for the slope. Create a scatter plot of the data. So then just click here, click this next arrow, and you will see the scatter plot. So as you can see here, the scatter plot is like this. Looks like quadratic. You know, it looks like a parabola. You know, started as if it's going linear, then it began to curve like a parabola. So you know, when you check these graphs with this, it's this actually. B is the correct option. So the next one, identify a characteristic of the data that is ignored by the regression line. So if you read these options, you will see that the data has a pattern that is not a straight line. It's, you know, it has a curve like a parabola. So it's gonna be option B. Question 5. Using the pairs of values for all 10 points, find the equation of the regression line. B. After removing the point with coordinates 1, 2, use the pairs of values for the remaining 9 points and find the equation of the regression line. Compare the results from parts A and B. So let's pull up Notepad. Let's pull up Notepad so we can get these points. So I'm gonna just type here x, y, x and y. The first point here as you can see this graph, let me show you this graph. If you make it bigger, if you expand it, this is the scale for the on the x-axis is 1 centimeter to 1 unit. That's the scale on the x-axis, 1 cm to 1 unit. And the scale on the y-axis is 1 cm to 1 unit as well. 1 centimeter to 1 unit is the scale on both axes. So we can now read our points. X is 1. When x is 1, y is 2. When x is, I can just make a line here. When x is 3, y is 5. When x is 3 again, y is 6. When x is 3 again, y is 7. Then when x is 4, y is 5. When x is 4 again, y is 6. When x is 4, y is 7. When x is 5, y is 5. When x is 5 again, y is 6. And when x is 5, y is 7. All right. I'm gonna use my calculator this time. Okay. Let's use my calculator this time. So I'm just gonna go to my website. You can go to chukwuemekasamuel.com. That's fine. Go to portfolios, and in this video we are going to use correlation and regression calculator. Correlation and regression calculator. We are going to we can use in this calculator, you know, let me talk about this for a moment. I solved this, you know, we have two formulas to find the linear correlation coefficient. So we can use any of these two formulas. It will give us the same thing. If you were taking this class online, in class, if you were taking this course in class, then your professor will most likely want you to show all your work. And this is the way you can check your work to show whether you got all the steps right. Your professor most likely will want you to set up a table for the x and for the y and for all these steps to calculate it. So you can kind of use this to check whether you make any mistake in any step. If you're taking this in class. So I'm just gonna make this to be on the same page here. So we can put in this, our x values, separate each value with a comma. Do not put a period at the end. So for the x we have 1, 3, 3, 3, 4, 4, 4, 5, 5, 5. For the y we have 2, 5, 6, 7, 5, 6, 7, 5, 6, 7. Yeah, please do not put a period or comma at the end. Then it says here, use 5% significance level if you're not given. I know here they didn't give us the significance level, so we're gonna use 5%. That's fine. So just put 5%, 5, select percent. If you're gonna use decimal, you put 0.05. Yeah. And then you just click this, calculate. So if you look at this, it gives you the whole steps. Like it gives you the whole steps. When you just need to put in x and y, that's all. And then the significance level. and it gives you the other steps. So you read this here. It gives us the Pearson linear correlation coefficient. Gives us the critical value right away. Gives us the absolute value of the correlation coefficient. Like the absolute value is greater than the critical value. So tells you, okay, that there is a positive linear relation between the variables. Tells you the slope, tells you the y-intercept, then gives you the least squares regression line. So we're gonna look at this now and just put in this. We can make this to be side by side. We now have the y-intercept first to 3 decimal places is 2.766, and then the slope to 3 decimal places as needed is 0.766. Then what is the equation of the regression line for the set of 9 points? For the set of 9 points. So if you want, you can just remove this last point and click calculate again. It will change it will give you the updated result. But I don't want that, and I don't advise you to do that. It's always good if you refresh after each calculation, just reload the page to remove these results, because sometimes JavaScript is funny sometimes, and it depends on your browsers. So after each calculation, it will be good if you refresh your browser. That's my advice. And then when you refresh your browser, these results might still be here. Just click reset. If you click reset, it will clear all these entries. But I have a second formula anyway. So I have a second formula for finding the correlation coefficient. And some people might ask me, what's the difference, since it gives you the same results? Well, the first formula, you will have to find the mean and standard deviation, because the mean and standard deviation is used in the calculation. Second formula does not need the mean and standard deviation. Some people prefer the second formula, but the first formula is more popular. But believe you me, the second formula is preferred by some folks. So what I'm gonna do is I'm gonna remove, because it says for the set of 9 points, we have to remove 1 and 1, 2. We have to remove 1 from X and 2 from Y, and then we find the regression line for the set of just the 9 points. So what I'm going to do is I will just grab this right here. I'll forget about 1. Copy this. Copy. Go to the second formula and paste it here. And then I'm gonna grab for the Y. I'll just grab this here. Copy. Go here. Paste it. Then I'll put 5% significance level, and I'll press calculate. So it fills up all these, it populates that. Then I can answer this now. What would be the equation of the regression line round to 3 decimal places? So if you read this here, it tells you that there is no linear relation exists between the variables. Only with the set of 9 points, you don't have any relation between the variables. So because no linear relationship exists, the sample mean for the Y, which is 6, which is equal to 6, is used as the predicted Y for any value of X. So this is just 6 here, 6. Then the next question. So it's good after finishing any calculation, just refresh this, refresh it. Choose the correct description of the results below. As you can see here, the removal of the point has a significant impact on the regression line. With that point, we had a positive linear relation. Without the point, we didn't have any relation at all. So the removal of the point has a significant impact on the regression line. Question 6. The data show the time intervals after an eruption to the next eruption of a certain geyser. Find the regression equation letting the first variable be the independent or the x variable. Find the best predicted time of the interval after an eruption, given that the current eruption has a height of 86 feet. Use a 5% significance level. So we're going to use Statcrunch turn of Statcrunch. So I'm going to just click here, open in Statcrunch, and let's put this side by side. So this is our x and this is our y. The height is our x, and the interval after eruption is our y. You can click here. Interval after is our y, and then the height is our x. So we go to start, regression, simple linear. Get our x, that's the height. Get our y. It wants us to predict the best predicted time if the height is 86. So you come right here, prediction of y, and you have the level 0.95. 0.95 confidence level. So significance level of 0.05 is the same right now, here as confidence level of 95%. Okay, significance level of 5% is the same as the confidence level of 95%, because a confidence level plus significance level is equal to 1. So your Statcrunch leaves it as 0. This level is confidence level, it's not significance level. So don't change 0.05 here, no, leave it like this. And then the prediction of y for what x value? 86. So you type 86 here. Excuse me. You type 86 and you press compute. Then you can look at it here. This is your regression equation right here. That's your regression equation. Your y interval after, that's the time, equal to the y-intercept plus the slope times the height. The height is the x. So you put that to 2 decimal places. This will be 37.46, and the slope will be 0.39. Then the best predicted time for the interval after an eruption that is 86 feet high. So just scroll down. Okay, go ahead and scroll down here. When you scroll down, you see predicted values. And for x value of 86, the predicted y is this. Okay, so this is a 70. To 1 decimal place, it will be 70.8. Okay. Next question. We are done with this question 6. Okay. Question 7. My turn. My calculator's turn. The data shows systolic and diastolic blood pressure of certain people. Find a regression equation letting the systolic reading be the independent variable, which is your x variable. Find the best predicted diastolic pressure for a person with a systolic reading of 111. Is the predicted value close to 86.7, which was the actual diastolic reading? Use a significance level of 5%. So I'm gonna just, let's use my calculator. So when you if you refresh this, these values are still here. The only thing that leaves is the answer. So just click reset. Doesn't matter, just click reset. And I'm gonna reset both of them. So just click reset. So we go ahead and type in the data. For X, we have 142, 114, 114, 133, 148, 143, 116, 116. For the Y, we have 79, 86, 61, 71, 82, 79, 87, 58. And they asked us to use 5%. So you can also use 0.05, but you have to set this in decimal. Don't use percent, because that's in decimal here. And just scroll down and click calculate. So it gives you everything here. The regression equation, the y-intercept to 2 decimal places is 47.02, and the slope is 0.22. Best predicted diastolic pressure for a person with a systolic reading of 111. If you read here, it says here, therefore no linear relation exists between the variables. And when no linear relation exists between the variables, the best, the sample mean for the y is the best predicted y for any x. So to 1 decimal place, that would be 75.4. 75.4. Okay, we'll just refresh this. Is the predicted value close to 86.7, which was the actual diastolic reading? It's not close. It's not close to the actual diastolic reading. It's not. So we'll just put it's not. Question 8. Statcrunch. The data show the chest size and weight of several bears. Find a regression equation letting chest size be the independent variable. Then find the best predicted weight of a bear with a chest size of 48 inches. Is the result close to the actual weight of 518 pounds? Use a significance level of 0.05. So we click on this icon, open in Statcrunch. We'll get this side by side here. So we go to Start, Regression, Simple Linear. X is the chest size, we get it. And the Y is the weight. They asked us to predict, they asked us to use 5% significance level. And that is the same thing as 95% confidence level. So leave this as is. The chest size of 48. So we put 48 here. And we click compute. So this is the regression equation right here. To 1 decimal place, the y-intercept is negative 186.8. And the slope is 13.6. Best predicted weight of a bear with a chest size of 48 inches. So you scroll all the way down, and to 1 decimal place, the best predicted weight is 468.4. You know, and when you're finished with Statcrunch, you can just close it right away. Close it. Is the result close to the actual weight of 518 pounds? No, it's not. The result is not close. So option B is most likely the choice in this case. So it's not close to that. Question 9. The data show the list and selling prices for several expensive homes. Find the regression equation, letting the list price be the independent variable. Find the best predicted selling price of a home having a list price of $2 million. Is the result close to the actual selling price of $2.1 million? Use a 5% significance level. So, my calculator. Okay, we are going to, let's use the second formula this time. It doesn't matter. Whether you use any of the formulas, it will give you the same answer. So we have 3.5, 2.6, 2.5, 1.5, 2.5, 3.9. And for the response variable, the values are 4, 3, 2.6, 1.6, 2.8, 4.1. Significance level of 5%. And we scroll down, we click compute, calculate. So the y-intercept of the regression line is to 4 decimal places as needed. As you can see it here, it says it here. Right here, y-intercept. So y-intercept is 0.0219. And the slope is 1.0890. 1.0890, or you just put 1.089, it doesn't matter. What is the best predicted selling price of a home having a list price of $2 million? So if you read this here, we see that there is a positive linear relation between the variables. So we're going to use because there is a positive linear relation between the variables, we will use the regression equation to predict the value of the response variable for the given value of the predictor variable. So what I'm going to do here is this. So if you scroll up, you see here predicted y and residual. You see this right here, predicted y and residual. Okay, this is the calculator to use to find the predicted y. That is when there is a relationship. If there's no relationship, it will tell you what to use. So see what I'm going to do. I'm going to grab this right here. Just grab the slope. Copy. Please don't round. Okay, do not round. Do not. You only round at the final answer. So I'm going to take this as it is. As you can see, my calculator is very precise. I mean, it gives you a lot of decimal places. So if you want the most accurate answer, you know, you go with my calculator. Okay, so I'll copy the slope. So I'll come here, I'll right click and paste it. This is the slope. And I'm gonna go grab the y-intercept. Yeah. Otherwise, we're gonna use calculator to solve this, but I mean, I'm just wanna use technology to solve it. So I'm gonna paste this here, and then for the x, it asked us x here is 2. X is 2, so our x is 2. You don't need anything here. You know, if you want to find the residual, then you put something here. Otherwise, I mean, we're not calculating the residual, so it will treat this as 0. That's fine. You press calculate, and it gives you the predicted y. See that? The predicted y. So to 2 decimal places, the predicted y is 2.2, because it's 2.19999, so it's 2.2. 2.2. Then I just refresh this. Yeah, it's always good to, after each calculation, refresh it to remove the result. You know, just do that. Now, is 2.2 close to 2.1? It's close. It's close. It's close. 2.2 million is close to the actual selling price of 2.1 million. Yeah, it's close. Question 10. Statcrunch. Find a regression equation letting overhead width be the predictor variable. That's the x variable. Find the best predicted weight of a seal if the overhead width measured from a photograph. Find the best predicted weight of a seal if the overhead width measured from a photograph is 2.2 centimeters. Can the prediction be correct? What is wrong with predicting the weight in this case? Use a significance level of 5%. So let's open this on Statcrunch. Put this on the same window. All right, so go to Start, Regression, Simple Linear. Our x is the overhead weight, y variable is the weight. And we want to predict find the best predicted weight if the overhead weight is 2.2. So you just put 2.2 here. And you press compute. So this is the regression equation right here. The y-intercept to 1 decimal place is negative 215.8. And the slope is 52.4. The best predicted weight for an overhead weight of 2.2 centimeters is what? So we scroll down, and to 1 decimal place it will be negative 100.6. Negative 100.6. As you can see here, predicted y. Okay, now close this. Can the prediction be correct? What is wrong with predicting the weight in this case? We cannot have a negative weight. We can have a negative weight, as you can see here. And if we check 2.2, 2.2 is outside the data. You know, you actually use this least squares regression equation if you find out, number one, that there is a relationship. It could be a positive linear relationship or negative linear relationship. That's number one. Number two, if the predictor variable or the explanatory variable, the given value, if the given value of the explanatory variable is within the scope of the data for which you found a regression equation, 2.2 is outside the scope. So if you look at these options here, let's see. The prediction cannot be correct because a negative weight does not make sense. The width in this case is beyond the scope of the available sample data. Yeah, that makes sense, you know. And you can read the other ones, take time and read the other options. But the correct option would be A. A negative weight does not make sense. The weight is beyond the scope of the data. So, question 11. My calculator. Listed below are systolic blood pressure measurements in millimeter mercury. This is known as mercury, Hg. That's mercury. That's the chemical symbol for mercury. Listed below are systolic blood pressure measurements in millimeter mercury obtained from the same woman. Find the regression equation, letting the right arm blood pressure be the predictor variable. Find the best predicted systolic blood pressure in the left arm, given that the systolic blood pressure in the right arm is 100 millimeter mercury. Use a 5% significance level. So, I'm going to reset this. Let's use the second formula here. That's fine. The data, let's get the data. For the X is the right arm, Y is the left arm. So, this is, for the X is 102, 101, 94, 79, 79. For the Y, we have 174, 169, 145, 147, 146. And they asked us to use a 5% significance level, 0.05 decimal. And you scroll down and you click calculate. So the regression equation, the y-intercept of the regression equation to 1 decimal place is 64.3. The slope to 1 decimal place is 1. Because it's 1.0. So 1, you can set 1. There no linear relation exists between the variables. So because no linear relation exists, the best predicted value would be 156.2. 156.2. Okay, I'll refresh this. Question 12. The data show the bug shapes per minute at different temperatures. Find the regression equation, letting the first variable be the independent variable. Find the best predicted temperature for a time when a bug is shaping at the rate of 3,000 shapes per minute. Use a 5% significance level. What is wrong with this predicted value? So we use Statcrunch. Open this in Statcrunch. We go to Start, Regression, Simple Linear. Our X variable is shapes in 1 minute. Y variable is the temperature. And they asked us to predict the Y when X is 3,000. This is at 5% significance level, which is the same thing as 95% confidence level. So you leave it like this. And you click compute. Extend this. Your y-intercept, they said round the x coefficient to 4 decimal places as needed. The x coefficient is your slope. And then round the constant to 2 decimal places as needed. The constant is the y-intercept. So the y-intercept to 2 decimal places would be 43.15. The slope to 4 decimal places would be 0.0380 because it's 0, 1, 2, 3, 4. So 0.0380, or you just put 0.038. What is the best predicted temperature when x is 3000? So scroll down. So predicted y, correct to 1 decimal place, is 157.1. And close this. What is wrong with this predicted value? So let's see here. X is 3000. As you can see here, we don't have 3000 is beyond the scope of this data for the X, because we have 968, 1089, 826, 820, 1102, and 806. 3000 is beyond the scope. So let's see here. It is unrealistically high. 157.1 degree Fahrenheit. That's a lot. That's very hot. Very, very hot. Now, you know the normal human temperature, normal human body temperature. The normal human body temperature is 37 degrees Celsius or 98.4 degree Fahrenheit. Now, this is 157.1 degree Fahrenheit. That's very hot. So I would say it's unrealistically high. The value 3000 is outside the range of these X, which is the observed values. So I would go with C. Question 13. My calculator. The data showed the number of viewers for television stars with certain salaries. Find the regression equation, letting salary be the independent variable. Find the best predicted number of viewers for a television star with a salary of $13 million. Is the result close to the actual number of viewers, 5.7 million? Use a 5% significance level. So let's reset this. We can use second formula, that's fine. You can go ahead and reset this first formula. So the X we have here, we have 98, 14, 2, 11, 11, 7, 14, and then 1. For the Y, we have 3.2, 9.1, 4.6, 10.8, 10.7, 6.3, 2.9, 4.4. Significance level of 5%. Calculate. So the y-intercept of the regression line to 3 decimal places, y-intercept is 7.192, and the slope to 3 decimal places is negative 0.035. Negative 0.035. Best predicted number of viewers for a television star with a salary of $13 million. So no linear relation exists between the variables. So the best predicted y to one decimal place will be 6.5. 6.5. 6.5. Okay, we'll refresh this and we'll make this bigger. Is the result close to the actual number of viewers, 5.7? No, it's not close. So it's not close. So I would say this, it's not very close to the actual number of viewers of 5.7 million. Question 14. Statcrunch. Find a regression equation letting the diameter be the predictor variable. Find the best predicted circumference of a marble with a diameter of 1.9 centimeters. How does the result compare to the actual circumference of 6.0 centimeter? Use a 5% significance level. So we open this in Statcrunch. We go to Start, Regression, Simple Linear. Our x variable is the diameter, y variable is the circumference. The predicted, they want us to predict y for x value of 1.9. 1.9. And you press compute. See that here? So the y-intercept of the regression equation, this is the regression equation. The y-intercept to 5 decimal places as needed will give us 0.01686. 1, 2, 3, 4, 5. 0.01686. And the slope to 5 decimal places as needed is 3.140, because this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 8 is, yeah. So 1 plus 59 is 6. So you can just 3.1406. If you want to put 3.14060, that's fine. Still gonna work. Best predicted circumference. So scroll down here to 1 decimal place as needed. Will give us 6 because this is 8 is more than 5. So just gonna give us 6 or 6.0. Doesn't matter because it says as needed. So how does the result compare to the actual circumference of 6? Oh, it's the same thing. As you can see here, it's the same. So let's see here. Even though 1.9 centimeter is beyond the scope of the sample diameters, the predicted value yields the actual circumference. Yeah, 1.9 is beyond the scope because this is 7.5, 24.5, 4.4, 22.2, 6.9, 4.1, 20.6. So yeah, 1.9 is beyond the scope, but the predicted value actually yields the actual circumference. Wow. Okay. Since 1.9 is within the scope, no, it's not. Even though 1.9 is within the scope, no, it's not. Since 1.9 is beyond the scope, the predicted value yields a very different circumference. It did not. It yielded the same. The predicted one is 6 and the actual one is 6.0. Is the same. So A is the correct option here. My calculator. Use the data consisting of an IQ score and brain volume. Find the best predicted IQ score for someone with a brain volume of 1000 cm cube. Use a 5% significance level. Hey, let me see the, okay, this is, the data set is what I'm looking for. There you go. This is too much to type. This is too much to type. I know I said my calculator, but I guess we'll use Statcrunch in this case because it's too much to type with my calculator. So let's use Statcrunch. Okay, I'm going to open this in Statcrunch. And let me put this in the same window. All right. We go to Start, Regression, Simple Linear. X is the brain volume, Y is the IQ score. And we want to find the best predicted IQ score for someone with a brain volume of 1000 centimeter cube. So come here, you put 1000 here. Compute. The y-intercept of the regression equation to 5 decimal places as, okay, it says here, round the x coefficient to 5 decimal places as needed. That's the slope. Excuse me. And then the constant to 2 decimal places as needed. The constant is the y-intercept. So the y-intercept to 2 decimal places as needed is 131.2. Then the slope to 5 decimal places as needed is negative 0.01998. Negative 0.0, because this is 1, 2, 3, 4, 5, yeah, 1998. Okay. Then the best predicted IQ score for a brain volume of 1000 centimeter cube. Scroll down here to the nearest integer. So to the nearest integer here, as you can see, is 111. Okay, 111 to the nearest integer. Okay, sorry, that's not correct. Okay, so I don't know whether it's the problem of Statcrunch, which I don't know, or the thing with the Pearson here. Well, it's the same company that owns both of them anyway, Pearson. So we tried 111, it didn't work. Just put 112. Put 112. But to the nearest integer, as you can see here, is 111. But just put 112. Just put it 112. Oh wow! It says 112 is still wrong as the predicted y. Seriously. Okay. Let's use my calculator. Let's use my calculator because I don't wanna. If you do this 3 times again, and I don't want to. If you do this the 3rd time and it's wrong, then it will be a whole new question. So I'm just gonna use my calculator. I use my calculator, and this is question 15. Okay, let's use my calculator, folks. Let's use my calculator and do it. I will go ahead and type this. Reset this here. Okay, for the x I have 1327, 1358, 918, 1470, 1187, 1217, 1254, 1333. And let me go ahead and type this for the y here. 89 105. Before I scroll down, okay. 129 93 122 119 107 128. Okay, then let's complete this. Here for the x, I have 1310 1197 941 1122 984 1056 904 1093, and for the y 110 114 125 125 91 83 110 90. Okay, then here for the x, put a comma. After each value, please put a comma. We complete it. 1288 1387 1128 1347, and then after 90 we have 103 82 104 119. Okay, and significance level of 5%, and then calculate. Oh wow, no linear relation exists between the variables. So probably what Statcrunch was doing. Who knows what Statcrunch was doing? I don't know. Statcrunch probably thought that linear relation existed between the variables. Let's see. Just to make sure. Maybe that was what Statcrunch thought. 1000. Actually, let me use the folks, let's do something. Let's make sure, okay? Let's make sure that Statcrunch is not wrong here. Let's see which one is wrong. Anyway, Statcrunch is wrong because I've tried to I've tried two things and it didn't work. Or maybe Statcrunch is not wrong, it might be the question, but let's see, okay? Let's see whether Statcrunch thought that there was a linear relation when there was not. So if I do let me clear this. 0.01997 9598 times 1000 equal to. Okay, I'll save this in memory. I'll save it in memory, and then I do 131.1967 minus recall the memory equal to. Yeah, Statcrunch did it as if there was a linear relationship, and that's why. But my calculator says otherwise. My calculator says that there is no linear relationship. That's what my calculator says. Yeah. So I beat Statcrunch to this. Let me make sure. Okay. The best predicted IQ score in this case will be 107.4. Okay, to the nearest integer will be 107. 107. Yo! I got it correct, folks. Hey! Thank God. Thank God. Thank you, Jesus Christ. Thank God. So you see here, I got it correct. You see now, my calculator is good. See that? I'm gonna make a note on this right away. Question 15 of this video, and I'll probably contact Pearson about it. I hope they recognize me, right? Hey, I hope they recognize me, right? I hope they recognize me, right? Yeah, of course. You see, because I found out the Statcrunch is giving wrong answer. Okay, and you know, we are, like I said, I've been saying, we are human beings. We make mistakes. Only God does not make mistake. Only God. See, so we are human beings. Man, it's human being that developed the Statcrunch. It's human being. We all make mistakes. We make mistakes. We are human beings. Only God does not make mistake. So, yes. So in this case, if you do it with Statcrunch and it's wrong, do it with Mr. C's calculator. Do it with Sam Don for Peace calculator. Do it with Samuel Chukwuemeka's calculator. Or do it with Samuel Dominic Chukwuemeka's calculator. Okay, I'm going to refresh this. Let's go to the next question. Question 16. Listed below are paired data consisting of movie budget amounts and the amounts that the movie is grossed. Find a regression equation, letting the budget be the predictor variable. Find the best predicted amount that a movie will gross if its budget is $100 million. Use a 5% significance level. This is a long data. Let's do it with Statcrunch. Okay, let's go ahead and do it with Statcrunch. The data is too much. So I'm going to open in Statcrunch. And we get start, regression, simple linear. So x variable is the budget, y variable is the gross. Predicted. Find the best predicted amount that a movie will gross if the budget is $100 million. So you come here, put 100, and click compute. All right. So the regression equation, the y-intercept of the regression equation to one decimal place is 19.8, and the slope to one decimal place is 1.3. Yep. Then the best predicted gross for a movie with $100 million budget to one decimal place will be 150.9. 150.9. Yo. Question 17. 50 matched pairs of magnitude/depth measurements randomly selected from 10,594 earthquakes recorded in 1 year from a location in Southern California. Okay, you would think that the English here, they need to, is shown in the table. Okay, find the best predicted depth of an earthquake with a magnitude of 1.1. Use a significance level of 0.05. This is 50 pairs of data. That's a lot. That's a lot. So let's use Statcrunch. Let's go ahead and use Statcrunch. go to Start, Regression, Simple Linear. X variable is the magnitude, Y variable is the depth. They want us to predict the depth for a magnitude earthquake with magnitude of 1.1. So we put 1.1 and leave it as 95% confidence level. Compute. So the regression equation, the y-intercept to 1 decimal place is 12.8. And the slope to 1 decimal place is negative 0.8. Okay. Then the best predicted depth for a magnitude of 1.1 is to 1 decimal place as needed. So this is just 12. Okay, this just put 12 or 12.0, it doesn't matter. Okay, let's try 12.0 kilometers. 12.0. Okay, because I don't want to have a new question now. So I'm going to do this with my calculator. I know that I'm going to do this with my calculator, folks, to see. It might be another case whereby they thought that there is a relation, a correlation between the variables, but there's not. I don't know. Let's I'm gonna reset this. Let's go ahead and put in this data. The magnitude, this 1.65, 2.71, 0.07, 0.03, 2.26. Now another thing you can do is, you know what, another thing we can do is to use Statcrunch and find the mean of the y. That's another thing we can do. Okay, that's another thing we can do. I'm gonna show it to you anyway, but let me use my calculator first. Let me use my calculator because I'm more confident with my calculator than using Statcrunch, because I wrote this myself. I developed this calculator myself. I thank God I did it myself. So I'm more confident with it than Statcrunch. So let's go ahead and put in this 2.55, 2.29, 2.51, and later, if it works out, then I'll show you how you can use Statcrunch to find the mean of the sample mean. Actually, we've done that in previous videos, but I'll show you. Okay, for the y here, we have 8.8, 7.5, 8.9, 5.5, 9.3, 7.3, 5.5, 10.9, 5.5, 10.9. If you're typing this, just be careful. Be careful. Okay, so the next one, 1.77, 0.79, 1.46, 0.04, 0.52, 1.35, 1.99, 2.81, and here 6.8, 5.2, 12.3, 13.8, 13.3, 11.5, 5.8, 14.4. Okay. Then here we have 2.69, 0.33, 1.26, 1.11, 1.06, 2.33, 0.38, 2.57, 2.75. Here we have 10.3, 13.1, 11.2, 7.7, 13.7, 17.9, 17.7, 7.8, 7.5. Then here we have 1.23, 1.16, 2.37, 0.55, 2.24, 2.54, 2.38, 0.43. Here we have 18.9, 17.4, 16.7, 19.6, 10.9, 10.9, 19.7, 14.6, 13.1. Then here we have 0.84, 0.22, 0.52, 2.45, 0.68, 2.31, 0.07, 1.66. Here we have 2.7, 16.1, 6.8, 8.1, 12.4, 7.6, 6.3, 7.5. Here we have 0.86, 2.64, 0.53, 0.31, 0.85, 2.65, 1.07, 1.35, 0.24. Here we have 16.9, 6.3, 13.2, 18.3, 11.9, 17.7, 14.6, 15.9, 17.7. Okay, that's it. So just delete this last comma. All right. Okay, I pray to God I get this right. Now 0.05 in decimal, and then calculate. So no linear relation exists between the variables, none. Yeah, probably Statcrunch is treating it that there is the linear relationship that is this. All right, folks, let's go ahead. The best predicted depth in this case to one decimal place will be 11.7. 11.7. Yo! Thank you, Jesus Christ. Thank God. All right. Let me show you guys, I know this is a lot to type, and, as you can see the whole thing, assuming you mess up one place, you can see the whole thing, so you find out what to correct. And, you work on your typing skills anyway. All right, let's another thing you can do is this. See, another thing you can do here. Go to Statcrunch, open in Statcrunch, because when there is no linear relationship, then the best predicted y for any value of x is the mean of the sample of the response variable, the mean of the values of the response variable, the mean of the values of y. So go to, and now y is the depth. Okay, this is the x. So go to start, go to summary stats, go to columns, select only depth, only this, and select only mean, only, and compute. And you can see that that is 11.692. As you can see that it's 11.692. You can close this here. As you can see, it is 11.692. But what if they asked you more than one decimal place? That's another thing. What if they asked you, okay, round to 4 decimal places as needed? Then guess what? Mr. C's calculator. You see my... Oh, this is actual... Well, yeah, that's true. 11.692. Yeah, that's fine. JavaScript... Actually, this is not... No. The actual answer is 11.692, okay? That's the actual answer. But, you know, this calculator is more precise. I know JavaScript acts up sometimes. Like, you see these zeros. Just ignore it. This 11.692. And I'm not going to go into JavaScript scripting language. I know some programming languages give more accurate, well, more precise. I mean, this is accurate. It's just precise, precision. For this case, ignore the zeros, these zeros. So it's 11.692. Okay, next question. Let's close this. So I'm gonna also make a note on question 17. Okay, I will make a note on it as well. Okay, we are done with the calculations. Which of the following is not a requirement for regression analysis? The method for regression analysis line is not robust. It is seriously affected by a small departure from a normal distribution. Outliers can have a strong effect on the regression equation, so remove any outliers if they are known to be errors. That's right. Visual examination of the scatter plot shows that the points approximate a straight line pattern. That's right. The sample of paired data is a random sample of quantitative data. That's right. So not a requirement is gonna be A. It's gonna be A. Question 19, given a collection of paired sample data, the dash algebraically describes the relationship between the two variables x and y. Of course, this is the regression equation. Regression equation. Question 20, which of the following is not equivalent to the other three? Independent variable is your x. Predictor variable is your x. Explanatory variable is your x. Dependent is your y. That's your output. That's your response variable. So the answer is this, dependent variable. That's your y. Question 21. When making predictions based on regression lines, which of the following is not listed as a consideration? Use the regression line for predictions only if the data go far beyond the scope of the available sample data. No, you don't do that. If the data go far beyond the scope, you don't use regression line to make the prediction. So A should not be listed as consideration. Okay, best. B, use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables. Okay, that's right. Use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. And that's why we call it line of best fit. Yes, that's right. D, if the regression equation does not appear to be useful for making predictions, the best predicted value of a variable is its point estimate. Yeah, so A is the correct option here. Question 22. In working with two variables related by a regression equation, the dash in a variable is the amount that it changes when the other variable changes by exactly 1 unit. Oh, that's the slope. The slope. And the slope, of course, is the marginal change. Question 23. In a scatter plot, dash is a point lying far away from the other data points. Outlier, outlier, outlier. Question 24. Paired sample data may include one or more dash, which are points that strongly affect the graph of the regression line. That should be influential points. Question 25. For a pair of sample x and y values, the dash is the difference between the observed sample value of y and the y value that is predicted by using the regression equation. That's residual. Residual is the observed y minus predicted y. That is your residual. A straight line satisfies the dash if the sum of the squares of the residuals is the smallest sum possible. That is why we call it least squares. Least squares. The squares of the residuals is the smallest sum possible. Least squares property. Least squares line. Least squares. Question 27. A dash is a scatter plot of the xy values after each of the y coordinate values has been replaced by the residual value, observed y minus predicted y. You know, this y hat is the predicted y. That's a residual plot. Residual plot. Okay. And then you save your answer. All right. Folks, thank you so much for listening to this video. If you have any questions, please ask. If you want to contact Pearson as well, that's fine. Okay. You can make reference to this video. Yeah. When I have the time, I would also contact them about it. Thank you so much for listening, and you have a good night.